Today we are going to start a topic called collision theory. Okay? This is the last topic of our chapters. Okay. Now collision theory assumes some postulates. It has some postulates, and one by one we will discuss. See, first postulates of collision theory is the according to collision theory, the reactant molecules are assumed to be spherical in size. That means spherical. All the reactant particles are spherical, not in different shape. Okay. Second postulates. The number of collision per second, okay, per unit volume, per second, number of collisions per second per unit volume of the reactant, okay, reactants is known as collision frequency. That means what? Collision frequency is the number of collisions per second per unit volume. Okay. Now, if we take this one, A is a reactant, B is another reactant, which is in spherical in size. It gives product. Then the reaction rate is given by ZAB e to the power minus EA by RT. Okay, minus EA by RT. Here ZAB is the collision frequency, where ZAB is the collision frequency. Okay. The third postulate of this collision theory, written, no? You can take a screenshot and write. Okay. Third postulate says that the collision, okay, in which molecule collide with sufficient threshold energy. The collision in which molecule collide with sufficient threshold frequency and proper orientation. The collision between the reactant should have sufficient threshold frequency, threshold energy, and proper orientations so as to provide breaking or making of box. Then the collision is known as effective collision. Remember, effective collision. That means, in single word, we can say the effective collision is the collisions which have sufficient amount of threshold energy and proper orientations so as to provide the chemical bond formation on or chemical bond breaking to get our new product. Okay. Now here one term is there which is threshold energy. Now what is threshold energy? Threshold energy is the minimum energy, okay, is the minimum amount of energy which must be associated with reactant molecule to collide each other. Okay, threshold energy is the minimum amount of energy which should be associated with the reactant molecule to collide each other. Okay, next. Now let us take an example. Let us take a reaction where CH3 with methyl bromide when reacts with hydroxyl ion OH negative, it produces CH3OH methanol plus bromide, that is bromine. Now what is the mechanism? If you see the mechanism of these reactions, then suppose this one carbon, these three are hydrogen, and here is bromine. When this I negative, OH negative attracts this carbon, we will get two types of intermediate. Suppose first intermediate is first intermediate is this one. Becomes partially positive and partially negative. When OH negative, OH negative, that means a nucleophile approaches towards carbon, it should come near the bromine negative ion. Due to this negative charge, repulsion creates. That's why from this orientations, or you can say if OH negative comes from this side, reactions cannot happen. That means here no reaction. Okay. If this OH negative comes this way, then the orientation, this one is improper orientation. If OH negative comes from this way, then the orientation is, suppose this one hydrogen, this way. You can partially positive, partially negative, and we can say in middle one is partially positive, and both these two are partially negative. And this orientation, you can say proper orientation, and this results a new chemical bond making and breaking. That means product. This one proper orientations and results. Finally, this bonds break and this bond forms, and we get OH CH3 plus Cr negative. This is called the proper orientation, and this is called the improper orientations. Okay. Via this proper orientations, from this two reactant, we get the product methanol and bromine. But if the reactions proceed in this improper orientation, then we cannot obtain our desired product. Okay. As we finished our chapter, next thing we have to discuss some important question answers. Okay. Mainly in this chapter, we have to discuss mainly some numericals. Okay. Now see, here is the in-text question. Okay. The rate of a chemical reaction is double for an increase of 10 Kelvin in the absolute temperature from 298 Kelvin. We have to calculate activation energy. what will we do? See, first of all, write what are the given. Okay, write the given terms or given data. Okay, solution. Solution first, it is given T1. T1 is given 298. 298 Kelvin. T2 is 10 degree more, no? That means increase in 10 Kelvin. That means T2 is 298 plus 10 Kelvin. That means what? That means 308 Kelvin. Rate of chemical reactions doubled. Rate becomes double. If rate becomes double, okay, then what will happen? That constant also become double, no? K1. Let me see the question. Okay. Okay. Then suppose K1 is taken as K. Then obviously K2 becomes 2K, no? Since it is double. Now we had T1, T2, K1, K2. Now if we apply this formula, log of K2 by K1 equal to EA 2.303 R, okay, 2.303 R into T2 minus T1 by T1 T2. Then we get log of this one. Log of K2. K2 is 2K. And K1 is single K. This one EA by 2.303 R. R is the gas constant. T2. T2 is here is given 308. 308 and 298 T1. And this one 298 into 308. Now if we calculate, then it becomes K cancel, log 2 A 303. This one is 10 and this one if you just multiply you get 298 into 308. I didn't multiply in these steps. Okay, see the next steps. Let me know. Okay, you can take a screenshot. Okay, then in the next step, if you just simply multiply and divide, you get, I did not multiply. Okay, I'm just writing directly the answer, but you just calculate. Okay, calculate the EA. You have 2.290 Kelvin, kilojoule per mole. 2.290 kilojoule per mole. Next question. Next question in your exercise. In your exercise, okay, from your exercise is question number 14. Exercise question number 14. Exercise question number 14 is given that the half-life for radioactive decay of carbon 14 is 5730 years. An archaeological artifact containing wood had only 80% of the carbon 14 found in living trees. Okay, then estimate the age of the sample. Okay, now see what is given. What is given? Decay constant. That means the rate constant. Simple. The rate constant, as you know, rate constant K. Okay, K is 0.693 by T half. Here it is assumed as a first order because the radioactive reactions cannot complete, or radioactive elements take infinite time to complete. That's why we are taking the first order half-life period equations. Okay, now see. Then this one, then 269, no, sorry, 0693, and T half, that means T half, not T half, the half life of radioactive decay is given that 5730. 5730. Now 5730, what? 5730. If we put 5730 here, and we get what? This one, ER inverse. Okay, ER inverse. Now this one we found K, that means rate constant. Now as we know, T for fast order reaction is the 2.303 divided by K log of R naught divided by R. R naught divided by R. Then obviously 2.303. This one K, if you put 0.6 times 3 divided by 5730, okay? 5730 into log of, this is the main thing. R naught was the concentration at the initial positions. Okay, initial positions. Remember, when time is 0, that means the reaction did not start. The concentration of the reactant should be 100%, no? Because the reaction did not start. That's why here is we have written 100. Since it is given in 100%, but after some time, that means after half life, it becomes 80%. Here is 80. Then it becomes 0, 0. Now, if we calculate these two numerical terms, that means that just simply the division multiplication, you get 1845. Yeah, this one is the answer. Okay. Next. Next question from our exercise is the question number 18. Exercise question number 18 is given that for a fast order reaction, show that time required for 99% completion is twice the time required for the completion of 90% of reactions. Okay, see, for a fast order reactions, we know T equal to 2.303 divided by K log of, here is a new formula, okay, A by A minus X. A by A minus X. A is the initial concentration, okay, initial concentration of the reactant, and A minus X. X is the decrease in concentrations of reactant at time T. A is the initial concentration. Okay. Now, you can use R naught by R in place of this. Okay. You can use R naught by R in place of this. I will explain. Okay. I shall explain how it is same. Now, it is given that 99% completions means this X is 99. No, X is 99%. Okay. When the reaction is completed by 99%, that means X is 99%. That's why T equal to 2 point, therefore T equal to 2.303 by K log of A. A means 100%, no? 100%. Divided by 100% minus 99%. Then it becomes 2.303 by K log of what? Log of becomes 100 divided by 1. Okay, 100 divided by 1 means 100 divided by 1 means 100 square. Okay, then 2.303 divided by k, and log of tan square equal to what? Okay, log of tan square equal to 2. Log of tan square equal to 2. This one for 99% completion. Now let us calculate the time for 90% completions. Wait. Now for 90% completions. Okay, this one T for 99%. This one 90%. 90% is again 2.303 divided by what? Divided by k log of a by a minus x. This one 2.303 divided by k, log of this one becomes 100, this one becomes 100 minus 90%, no? 90. Then it becomes 2.303 divided by k log of 100 divided by 10. That means only 10. And log of 10 is 1. This one. And it becomes 2.303 divided by k. Sorry, log of 10 means 1. If they given equation 1 and given equation 2, then if we just divide, okay, if this one is okay, my board is a little bit small, okay, that's why this one t 90%, this one t 99%. If we divide 1 by 2, 1 by 2, now 1 by 2 gives this one t 99% and this one t 99%. See, this one is same, no? Cancelled. If we divide, this one cancel, and it becomes what? It becomes 2 by 1. That is 2. That means t 99% equal to 2 into t 90%. Isn't it? That means t half to complete 99%. T 99% is equal to 2 into t 90%. Okay. Similar numericals in your question number, it is 17 and some others also, 17, 19. Okay, try to solve.